In this video, we'll look at two improvements to trees called bagging and random forests. We've previously seen how decision trees, constructed through iterative data splitting, are a unique and flexible class of predictive models. However, it turns out that by themselves, decision trees are not as accurate as we might have hoped because their flexibility makes them prone to overfitting. Not to fear, though, some small modifications to trees can make them very powerful. We'll explore two ideas for modifying trees in this video. The first idea is to use many trees instead of just a single tree. The motivation for this stems from the following idea. Growing a large tree with many splits is able to result in a suitably complex model. But as we know from the bias variance trade off, this high complexity is accompanied by high variance. In other words, large trees are prone to overfitting. It's natural to wonder if we can be greedy. Can we somehow keep our large, low bias tree but reduce its high variance? We can, actually. The trick is to average predictions from a lot of trees. This idea is rooted in the important statistical idea that averages can be much less variable than the original measurements. For example, the black trace in this figure shows the distribution of a given measurement, for example, height, over the individuals in a population. The red trace shows the sampling distribution of the mean of that measurement, for example, mean height, for a fixed sample size. Note how the width of the sampling distribution is much smaller than that of the original measurement. And larger sample sizes would result in a sampling distribution that is even more narrow. So in this context, the black distribution represents predictions from single decision trees, and the red distribution represents predictions resulting from averages of predictions from single trees. The theoretical idea of building many trees is nice, but how do we actually do it? When we've built single decision trees, we've used the entire training set. So, an initial idea might be to divide our training set into several parts so that we can build a tree on the data in each part. Unfortunately, this severely limits the sample size in each part, which would severely diminish the quality of the trees built for each part. A better idea, to not cut down so severely on the sample size for each tree, is to use a general statistical technique called bootstrapping. Bootstrapping is a procedure in which we resample our original sample with replacement many times to obtain several resamples of the same size as the original sample. For example, if our original sample had 1,000 cases, a bootstrap resample randomly draws 1,000 cases from the original sample with replacement, allowing any case to be drawn multiple times. So if we perform, say, B equals 10,000 resamples, bootstrapping will give us 10,000 samples of size 1,000. The sampling with replacement is critical because it allows different resamples to be produced each time. If we performed the resampling without replacement, we just obtain the original sample over and over again. So, bootstrapping is a general technique that is useful in a variety of situations. One main use for the B resamples is for statistical inference, understanding and quantifying the amount of variation or uncertainty present in an estimate. Another use of the B resamples in our particular use case with trees is an idea called model averaging or ensembling. This is the idea that predictions from many models can be aggregated, often via averaging, to create an overall better prediction. When model averaging or ensembling is implemented with bootstrapping, this goes by the term bagging, which is a combination of bootstrapping and aggregation of predictions via some type of averaging procedure. Bagging is not only useful for trees, any predictive model can be combined with bootstrap aggregation. This technique just happens to be particularly powerful for trees. The trees resulting from bootstrapping are also called bagged trees. To make all of these ideas precise, let's go over the bagging algorithm for trees. We first use bootstrapping to obtain a large number, B, of resamples from our original training sample. Using each resample, we grow a large, complex, so low bias, high variance tree. Finally, we average or aggregate the predictions from all B trees. This aggregation is different for regression versus classification trees. For regression trees, we take the mean of the B predictions. For classification trees, we take the majority vote of the B predictions. Let's look at an example of a bagged prediction in a regression setting, predicting house price from house features. Here we have 3 trees resulting from bootstrapping the training data, B equals 3 times, and we're looking to make a prediction for a case that has a living area of 3,000 square feet, 1 fireplace, and a land value of $50,000. So pause the video to verify that the predictions made by the 3 trees are as marked by the arrows. The bagged prediction of this house's price is the average of these 3 predictions. Let's look at an example of a bagged prediction in a classification setting, predicting heart disease from clinical characteristics. So first, verify the predictions made for the test case shown here. The majority vote aggregation here gives a bagged prediction of no for this patient's heart disease status. Now that we've discussed how bagged predictions are made, we can talk about an important computational idea regarding test performance estimation. We've used cross-validation throughout our course to estimate test or out-of-sample performance of our predictive models. Let's consider the steps involved in cross-validation in this new bagging setting. As always, we can start by randomly splitting the training data into k folds so that we can iteratively hold out one fold at a time for testing. For each of the k iterations, we use k minus 1 folds to train or fit the predictive model and use the remaining fold for testing. In particular, training the model in each iteration involves building a large number of trees, often 1,000 or more. Doing this k times is very computationally intensive. We'll address this issue in just a moment. But the training phase gives a model that we can use to test on data in the test fold. We generate bagged predictions for all test cases, and as we've shown with some examples, we can compute some sort of accuracy or error measure from these predictions. Finally, we aggregate the k error or accuracy measures resulting from the k iterations of cross-validation. The key takeaway here is that estimating test error using cross-validation takes a lot of time. Let's explore an alternative to test error estimation. Another method of error estimation is called out-of-bag, or OOB, error estimation. The idea behind this new method is as follows. So when we bootstrap, a given bootstrap resample is generally not going to contain all of the original training cases. For example, in bootstrap resample number 1, the resampling with replacement was such that cases 3 and 23 happened to not be chosen. This means that cases 3 and 23 weren't used to build tree 1 and can be used as a test set for that tree. Cases 3 and 23 are also called out-of-bag cases for tree 1. If we use a large enough number of bootstrap resamples, we expect that every training set case will serve as a test case for some tree, and likely several trees. This gives us an appreciable number of cases for testing our model. Let's look at a small example to illustrate the out-of-bag method for test error estimation. We have a training set of 6 cases, and we build a bagging model by bootstrapping 5 times to build 5 trees. The specific cases in each bootstrap resample are shown below each tree. So note that tree 1 is not built from cases 5 and 6. So cases 5 and 6 could serve as a test set for tree 1. Cases 1 and 6 form a test set for tree 2, and so on. The out-of-bag method steps through each training case one at a time and uses that case, if possible, as a test set. Let's look at what happens when we try to use case number 1 as a test set. Looking across the samples used to build each tree, we see that case 1 is used to train trees 1, 3, and 5. So case 1 is out of bag, the test case for trees 2 and 4. We use the bagging procedure to make a bagged prediction for case 1. This involves using trees 2 and 4 to make a prediction for case 1 and aggregating the predictions with either averaging or a majority vote, depending on whether the task is for regression or classification. We now have a fair test out of sample prediction for case 1. We know the true outcome for case 1, so we can compute an accuracy or error measure. We repeat this process for all training cases. Pause to verify the work shown on the bottom left, indicating what trees each case is a test case for. Ultimately, this process gives us a fair out-of-sample prediction for each case, and by comparing these predictions to the true outcomes, we can get an estimate of test error or accuracy. Notice how we only had to fit the bagging model once, rather than k times as in cross-validation, in order to estimate test performance. Out-of-bag error estimation is a much faster alternative to cross-validation and generally gives comparable estimates of test performance. So far, the one improvement to decision trees that we've explored is the idea of bootstrap aggregation, or bagging, in order to reduce the variance of predictions. It's worth considering if we can do even better than bagging. Let's take a look at the 3 regression trees in the earlier bagging model of house price as a function of house features. Note that all 3 trees first split on the living area variable, the square footage of the house. Note also that all 3 trees split on land value for both regions formed from the first split. The extreme similarity of the bagged trees actually motivates the second of the 2 improvements that we mentioned at the start of the video. The second improvement to decision trees is to encourage greater diversity in the trees. The statistical theory behind this idea is as follows. So as we discussed at the start of the video, averaging predictions does reduce the variance of the final prediction. However, averaging predictions that are highly related does not substantially reduce that variance. In bagging, the fitted trees end up looking very similar. This means that the predictions from the trees tend to be strongly related, and averaging these related predictions will only decrease the variance of the final prediction a little bit. We can try to increase the variance reduction of the averaging process by decorrelating the trees to make the predictions from the trees less related. This decorrelation is exactly the idea behind the random forest algorithm. Random forests are a small modification of bagged trees in which we promote decorrelation by forcing each tree to use different predictors. The random forest algorithm is identical to bagging, but when building each tree, only a random subset of predictors is allowed for consideration at each split of the tree. The size of this random subset is usually roughly the square root of the total number of predictors. So each time a split is considered, the recursive binary splitting algorithm only considers a smaller random subset of predictors when trying to find the best split, instead of considering all possible predictors. This prevents situations where all trees use the same few strongest predictors in the first splits. In the housing price example that we just looked at, this would have prevented the trees from all having living area and land value as the first 2 splits. In practice, bagging is never usually used alone. It's typically always combined with decorrelation as part of the random forest algorithm. This becomes particularly advantageous in situations where the number of predictors is huge, and a lot of these predictors are related to each other, which is multicollinearity. In summary, we've discussed how, by themselves, decision trees don't have the strongest predictive power because of their tendency to be overfit. However, two ideas greatly expand the power of trees. First, bagging, which is aggregating predictions from lots of trees with bootstrapping to reduce the variance of the final prediction. And two, using a diverse set of trees to decorrelate predictions and reduce variance even more. The coupling of bagging with decorrelation is the random forest algorithm. Finally, we noted a computational concern. Cross-validation is a rather slow option for estimating test performance, but out-of-bag error estimation is a much faster process with comparable results. Together, these ideas unlock a lot of powerful potential for trees.